This is question number 1 from your textbook using the trapezoidal rule. We're asked to use the trapezoidal rule to approximate the area here of the definite integral 0 to 2 of x squared dx. And we're asked when we use the trapezoidal rule to let n equal 4. The first thing we did here is that actually found the actual value here by doing the integration. So the area here is equal to 1/3 x cubed as evaluated from 0 to 3, and this is the fundamental theorem of calculus that we use. Got 2/3, which is equal to 2.75, I believe. 0, 0 when we look at the next one. So took that just as a kind of a measure to see when we get this answer to some basis of comparison, and start to use this. And so we're going to use the trapezoidal rule now. We're going to start off by saying that the area of x squared from 0 to 2 is approximately equal to this. And remember that we're going to get this front number by doing b minus a over 2 2n. But if you look at it, we get b minus a was 2 minus 0, isn't it? Here it is, 2 minus 0 over 2n, which is just 1 over n. We went back and it said we were asked to use n equals 4, so we got 1/4 right here. And this 1/4 is this 1/4 right here. It's our multiplier here. And then we're supposed to remember that there's this pattern, and the pattern goes 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, all the way to the second to the last term is still 2. The last term has a coefficient of 1. So we take the first value, which is 0, plus 2. Oh, again, we had a distance of 2 to cover, right? 0 to 2. We are going to break that into 4, so we had each piece would be worth 1/2. So 2 times 1/2 squared. Why 1/2 squared? Because our function is a squared function. 1/2 squared plus 2 again. 1/2 plus 1/2 is 1 squared plus 2 times 1 plus 1/2 is 3/2, isn't it? 3/2 squared. And now we're at our last piece, right? Because this is when we finally get to 2, right? We're going to 2. So we're going to get this 2 squared. All right? And then, frankly, we're just going to do the math. And the math, when you look at some of these, the math gets pretty outrageous. First thing you have to remember to bring this down. Then we're going to do this. Be careful not to cross cancel here. You can't do that because we have an exponent happening up here, don't we? So 1/4 squared, I'm sorry, 1/2 squared is 1/4, and 2 times 1/4 is 1/2. So 1/2 plus 1 squared is 1 times 2 is 2. This thing squared is 9/4. So we have 9/4 times 2. 9/4 times 2 is 18/4, which is 9/2. Isn't that right? So 9/2. So 9/2 here plus 2 squared is 4. All right. If you don't mind, I'm going to just clean this up a little bit for my own edification. 2 is the same as 4 over 2, isn't it? 4 is the same as 8 over 2, isn't it? Why am I doing that? So I have common denominators all the way across. Add these together, and we get 22/2. So we have 22/2, don't we? Oops, 22/2. That's the summation of all this stuff in here. Times this 1/4 is equal to 22/8, which of course is equal to 11/4, isn't it? So that simplifies to 11/4. If you put that into your calculator, you'll get back an answer like 2.6667 or something. So what am I doing here? What's the point? I'm trying to figure out how accurate is the trapezoidal rule compared to the actual. In this case, it was easy to take the actual. So here is the actual, and I want to compare that to this, and not perfect, but similar and close. Now what we're going to do in the next video is we're going to go back and we're going to use Simpson's rule to approximate the same area. And then we're going to compare that to this and this to that and see what happens. And again, we're going to try to prove out soon what happens as the number of n becomes large, as n approaches infinity, what happens to the accuracy. So stay tuned.